Yes.
Can you confirm that you can see my screen?
Yes, I can see your screen. It is perfect. Maybe something we can just remind the whole team, all the attendees, panelists, and participants. Uh, there is a Google link that was shared just before lunch hour. Please, if you need all the material, including what is going to be presented right now, including the notebook file that you're going to be using, all of this is in that particular folder, Google folder. So get it so that you actually can follow whatever the facilitators will be taking us through. Claire, back to you.
All right. Good afternoon, everyone. You're all welcome to the third Deep Learning Indaba conference. I think this is our first virtual event, and I hope you're excited and learning as well. So this afternoon, I'll be focusing on unsupervised learning, a type of machine learning. But maybe before I go into the specifics of unsupervised learning, I'll begin from a general perspective of machine learning so that we can be able to contextualize this very well. So machine learning is a branch of artificial intelligence, or if we're to generalize, we can say it's a subfield of computer science. And mainly it's around exploring the study and construction of algorithms that can help us to learn from the data and also be able to make predictions at the end of the day. And how does it come into place ideally? So if we've heard of the general part, which is artificial intelligence, where machine learning lies, under artificial intelligence, we basically aim at creating machines or agents or models that can be able to think and act like human beings, and also be able to think and act in a rational way. But what happens is that for us to be able to introduce these machines, there must be a component of learning. In other words, they must learn. So for example, if I have a medical personnel and I'm interested in designing a machine that is going to act as a medical personnel, maybe depending on the problem statement or the problem scope that I've been able to come up with. And ideally, let's say if I give an example of a country, let's say the problem that I'm addressing is that we do not have enough medical personnel in the rural areas. Let me give an example of that. And so maybe we think about using ICT in specific artificial intelligence to be able to address that problem. So for us to be able to come up with this machine, what happens is that we need to teach it what a medical personnel does. In other words, it needs to learn. And so the learning must happen on data. And I guess even from the previous speakers, they have highlighted something to do with data. It's very important because ideally the whole course is based on data. So, so for the machine to be able to act as a medical personnel, it needs to learn. And I'm assuming this medical personnel, maybe they are specialists in diagnosing malaria. So we can choose to train the machine on that specific problem. And so at the end of the day, it will be able to help us to distinguish between a malaria case and a no malaria case. Given a client or given a patient who has walked into the hospital, something like that. So such algorithms, they operate by building a model. And for example, we have some form of inputs that are made. And at the end of the day, we are able to come up with data-driven decisions or data-driven predictions rather than following a strictly static program that we've just built. So the learning ideally happens on the data. That's what I'm trying to say. And as a process, we could sort of like summarize it that we start by defining the objectives. And so these objectives are the objectives of the study. What exactly do you want the machine to do? What exactly do you want the model to do that you're trying to build? And that's what I highlighted earlier on, that at this point you need to come up with a problem. Because if you're not that specific in defining your problem, you'll find that it's a bit hard to also know the kind of data that you're going to pass into this model or into this machine. Because like I said, the learning is dependent on the data. So you need to be able to define your objective in that way to first of all, understand what exactly do you want to address, in that even as you go out to look for the data, you actually know what kind of data that you're interested in. Then the next step is to prepare the data. So if we look at the real world, we have a lot of data around us, and I guess the previous speaker highlighted on that. We have a lot of data, from sensor data to text data on different social media platforms, to data in form of image, in form of video, in form of audio. So there is a lot of data that is available, but that data contains a lot of noise. So for example, if we go to social media, we know basically people communicate a lot on social media. And even from social media, you can be able to understand people's sentiments. Ideally, for example, now that we are in this lockdown, what exactly are people talking about, etc. So imagining if you want to understand that from a population such as the Uganda population, you'll realize that you have to do what you call data preparation. And this involves different activities, from eliminating noise to eliminating what we would call outliers, because if you've ideally defined your problem scope very well, then you will be able to know that you have outliers. Outliers are sort of like data points that are not really of interest in the scope or in the subject that you're trying to address, the task that you're trying to address. Then we will also find that we have what we call future engineering or future selection. So what do we call data? The data in itself includes what we call the features and the label. Though as we migrate to unsupervised learning, we shall see a few changes, but it includes what we call the features and the label. If I go back to the malaria diagnosis case study, if I'm trying to design that, that type of agent that is going to help me to diagnose malaria, so I could choose to have symptoms as my data. And the choice is not basically dependent on the machine learning engineer or the data engineer. It's dependent on the doctor, because ideally you're trying to build something that you will deploy at the end of the day. And so it means that you need an expert. If I'm doing machine learning in health, it means I need an expert in health who is going to help me right from the point of helping me to sort of like narrow down to the data that is relevant, validate the data that I'm trying to use, even at the point of evaluating. So you'll find that you need to work with these different experts. If it's agriculture, you'll find that you need an agriculture expert, something like that. So the point of future engineering or future selection comes in whereby now you're trying to sort of like reduce the dimension of your data to focus on only the features that are relevant in predicting a given class. So for example, if I've captured so much information from the patient, there are those specific attributes that I've captured that actually can help me in diagnosing malaria. So it could be symptoms, a couple of symptoms that can sort of be like looped together, and you know that this person has malaria, or they don't have malaria, maybe you need to test for something else. So that point of future relevance is very important, because you'll find that in the process, if at all you have very many features that are not relevant, then it's going to affect the model performance, because it's going to try to generalize on every feature, yet some of these features are irrelevant. So that is also part of the data preparation process. And then the part of model building. So the learning in itself involves two stages or two phases. There is what we call the training phase and the testing phase. So still my colleagues have highlighted on this. So the training phase, under supervised learning, you must have heard of it, that this is where now you pass in what we call label deck examples. So in that case, a label deck example would be a data point and the desired label. So if I have, for example, 1,000 data points, and these are different records that I've captured, maybe from different health centers within the country, then I can choose to say, I'm going to train my model on 800 data points. So all those 800 data points under supervised learning will be labeled. So that at the end of the day, the machine can be able to learn how to map from a given input to a given output, something like that. Then after you've built your model, you've trained the model, it has learned the representations within the data. The next part is to test it. And that is where the predictions come in place. So when you're testing it, you're giving it unseen observations, you're giving it new observations that it has not seen before, because it doesn't make sense if we pull part of the training data and we test with it. Definitely that will not be learning, or it will not be a good assessment, but we do that prediction. So prediction, or the part of testing, you're basically now trying to find out, has the model actually learned? What exactly has it learned? Things like that. Then you definitely have to evaluate your model, because now the next point is you're going to deploy it, but you need to evaluate it. Evaluation is basically testing it. And I guess still different evaluation metrics have been highlighted, from accuracy to precision, recall, among others. Then once what you wanted to achieve has been obtained, you can go ahead and deploy the model. In other words, put it out for use in a real world environment. So I can't see the chat. I guess after this presentation, I'll come to the chat or the Q&A, then I answer the questions. Okay, so in real life, we've interacted with different machine learning applications. Like I said, still, if we are to generalize, we know that ICT is more of an enabler, meaning that it has been enhanced, or it has been used in different sectors to enhance a service delivery, and so on and so forth. So in real life, we have different applications where we've seen the use of machine learning. And this is just an example of one of them. For example, Netflix. So how does Netflix use machine learning? For those of you who have visited Netflix or any e-commerce website where there is sort of like a purchase of a good, a purchase and a sale of a good or a service. So what happens is that in human-computer interaction, or in user interface, you don't really want someone to spend a lot of time trying to navigate your website or trying to look for a product, something like that. It's a bit time consuming, but it also consumes bandwidth, and it's also a bit tiresome. So Netflix has what we call recommender systems, and these are built on machine learning. So the recommender systems, what they do is that they sort of like recommend, if I could put it like that. But to give a detailed explanation is that, you know, there are different movie types that are on Netflix. So I guess from horror movies to, what example? Okay, from horror movies, I'm assuming there is sort of like science and fiction, among others. So, so what happens is that if you have an account on Netflix, your logs can be captured, and the logs are sort of like the trails that you leave every time you leave the web, every time you visit the website, sorry. So your logs can be captured. The logs could include what kind of views do you make every time you visit the website. And apart from that, what kind of purchases do you make in case you've made a purchase before? So at the end of the day, if that information has been captured, then a data engineer in the back end can be able to understand your likes, your purchasing power, and also the kind of movies that you purchase. So that means that in case a new movie is coming up, sort of like those trailers that are normally produced before the actual movie comes out, as a trailer is coming out, if you visit your account again, you'll see certain recommendations. Maybe they are recommending this product to you, something like that. So in that process, I'm assuming that if Netflix has over 1 million movies, you don't really 1 million movies that have just been released today. Let me give an example. So you don't really have to waste a lot of time navigating through the 1 million to check for what you want. Why? Because there is an understanding, or there is an underlying algorithm that has been able to look at your previous logs, and then it has been able to recommend the different products that have been released, something like that. And so these other applications, I guess I captured these screenshots from Zindi, but these are the other areas where we've seen machine learning being used in real life. For example, here we have a challenge that is actually ongoing on Zindi, and it's about passion fruit disease detection. So ideally, can you be able to identify which passion fruit is diseased and which one is not diseased? In other words, which one is healthy? But just to summarize these screenshots from Zindi, so here we can see there is a case study of financial inclusion. Can you predict who in Africa is most likely to have a bank account? So there is that perspective of financial inclusion, still using machine learning. So here we have case studies around agriculture, which I think some of you might have heard about, from crop disease diagnosis to yield prediction, to also predicting what exactly are we using the land for, all those different elements. But then we also have AI in finance. And still not to waste so much time here, I guess if you've heard of Mocash, which is an MTN service product, I guess you must have heard of the fact that it is built around machine learning when it comes to predicting how much you're worth in terms of a loan and so many other things. So this is just a description to show us that there is machine learning in real life. Yeah. Okay, so having got an idea about the applications of machine learning and also what machine learning is about, we get to the different types of machine learning, because like we've indicated that we want to create agents, or to design agents that can think and act like humans, but at the same way think and act in a rational way or in a right way. So that means that machines sort of like duplicate the ways in which human beings learn. And according to this scholar, human beings majorly learn in 3 different ways. So there is what we call supervised learning, there is what we call unsupervised learning, and then there is what we call reinforcement learning. So the other types of learning, such as semi-supervised learning, are more of secondary types of learning, which try to merge more than one type of learning, something like that. So what happens with supervised learning? So with supervised learning, when the agent is learning, it gets examples that are labeled in a way that there is an input and output. So it is a pair, and the pair includes the features and the label. And then at the end of the day, it is able to learn a function that will get us from input to output, sort of like what we would call y is equal to f of x. So y is the label that we want to predict. And so we are saying that there is a function f that helps us, given this input, we can sort of like go to y, or to output y. On the other hand, unsupervised is just the opposite, of supervised learning. So with unsupervised, we are saying that we feed this model with unlabeled data. So what the agent does is that it learns the patterns in the input, even though there is no explicit feedback that is given to it. So it's just given x futures, or it's just given data that we call x. So x is the common variable. And then it has to learn the patterns within x at the end of the day, so that it's able to kind of like group a new instance or a new observation. So the most common example of this is clustering, which we are going to focus on in this presentation. And this would sort of be like, can we be able to identify or to detect potentially useful clusters of input examples? Still to continue with types of machine learning. So the other third type is reinforcement learning. So this one is a bit different from supervised and unsupervised. And how different is it? Is that here the agent learns from what we call a series of reinforcements. So these reinforcements are either positive or negative. And positive in a way that it will be a reward, and negative in a way that it will be a punishment. Yep. So for example, if we are looking at maybe a specific nation whereby giving a tip is mandatory. So for example, the agent has performed a particular task that it's supposed to perform, and it's not given a tip at the end of the journey. I'm assuming this is an AI taxi or a self-driving taxi, a self-driving car. So if it's not given a tip at the end of the journey, then maybe to it, that can be an indication that it did something wrong. So here we are assuming that tipping is mandatory, something like that. So the 2 points for a win at the end of a chess game tells the agent that it did something right. This is still another example. So this is a positive reward, this is a negative reward, okay? So it's up to the agent to decide which of the actions prior to the reinforcement were most responsible for it. And at the end of the day, depending on the reinforcement that it has received, then that will help it to better its performance the next phase or the next time this task is kind of like accomplished. So the reason why I say that these types of learning are common within human systems, because I think we relate with all of them. So reinforcement learning, ideally, if I kind of like give an example to kids, it's common, like that way of learning whereby your parent or your guardian will tell you that this is wrong. And maybe the negative reward in that case would be you're beaten or you're scolded, things like that. Then maybe if you do something good, such as you perform well, etc., then you're appreciated, depending on whatever way they would want to appreciate you, something like that. Then the other type of learning, which is not very common, but it exists, it's what we call semi-supervised learning. So with semi-supervised learning, we bring in aspects of supervised and aspects of unsupervised. And so that means that at the end of the day, we have a data set whereby part of it includes what we would use in a supervised learning way, and part of it includes what we would use in an unsupervised learning format. Okay. So still just giving an example of supervised learning. So if we are given a training set and we are calling this set variable n, which includes an input and output pair, so it would sort of be like this. We have each instance has x1 and y1, whereby x1, those are the features, and y1, that is the label that we would want the agent to learn at the end of the day. So x2, y2, something like that, up to xn. In other words, up to all the observations, all the instances that we have in the data. So here, each j is just a representation of the different instances. Each yj was generated by an unknown function, which is given by y is equal to f of x. And so ideally what we want to establish is that we want to discover that function h that approximates to the true function f. So in other words, in the prediction, we are saying that y is equal to h of x. So h of x in this case, it's this hypothetical function that we are trying to build using this model. And so we would want to approximate this h of x to the actual function, which is f of x. So this is the description that we have here. So x and y can be any value. They need not to be numbers. And I think still the previous speakers must have highlighted that you can have data in different formats, from numeric to text to audio, video, image, among other things. So learning is ideally searching through a space of possible hypotheses for one that will be able to perform well, even on new examples beyond the training set. And why do we think we have space of possible hypotheses. So if I look at an example, just visualize you've plotted your data on a canvas, and let's say like you have basically two categories. Let's say one you've color-coded it in blue, the other one you've color-coded it in red. And let's say that these are two different classes. So a classification problem, a machine learning agent that is addressing this classification problem, what we would want it to do is to find what we call a decision surface. But you might find a scenario whereby you can have, let's say, like over 5 decision surfaces. In this case, you have 5 different lines. So we need to find one which is going to be able to perform well even on new examples that are outside the training set. And so you'll find that there are different factors or parameters that you have to consider. Because first of all, you need, for example, in that case, if it's a binary classification problem, you need to look at that decision surface that is not close to either line. Because if you're going to go with a decision surface that is close to one class, then that means that you're more likely to be overfitting on one class and underfitting on the other class. But all those are different elements within that point when you're training your model. Then to measure the accuracy of the hypothesis, so now you've been able to create the model. So to evaluate it, you give it a test set because you need to see how is it performing on observations that have not featured. So you give it a test set of examples that are distinct from the training set. And at the end of the day, we say that it generalizes well if at all it has made a correct prediction over the value of y for these new examples, these novel examples that you have are within your test set. Okay, so like the previous speakers indicated, under supervised learning task, the problems or the tasks that we solve must lie under 2 categories. So it's either a classification task or a regression task. And ideally, you call it a classification or a regression depending on the type of Y, the type of output that you'd want to make. So if I'm looking at a categorical output, a discrete output, then that is going to be a classification problem. But still, like I've highlighted, that this classification problem can be binary or multi-classification problem. Binary, whereby you have 2 classes or 2 labels that you're predicting from, that it's either 0 or 1. In that case, it's either you have malaria or you don't have malaria. Then multi-classification, that's when you have like a couple of classes within. So for example, if I'm looking at it in the perspective of agriculture, I can say that this plant is diseased or it's not diseased. And that means I have 2 classes, diseased or healthy. But I can go ahead and break it down into a log granularity. In that case, I say if it's diseased, what diseases do I have? So maybe if I'm looking at one of the common plants, for example, crops, not plants, sorry. If I'm looking at one of the major or common crops within Uganda, I can maybe say, I can look at maybe cassava, and then I say, I'm going to look at a case of cassava mosaic, a case of cassava brown streak, a case of cassava green mite, and so on and so forth. So that means that I can have over 5 classes, over 10 classes, depending. Though on the other hand, you might be interested in a continuous output. So for example, if I'm looking at a financial inclusion problem where I'm going to do credit scoring, I can say that this person is worth a loan or they are not worth a loan. And that means that in that way, I'm looking at it as a classification problem. But I can look at it as a regression problem whereby if the model is going to say you're worth a loan, it's going to return how much you're worth. So sort of like to return a numeric value. So it's very hard for us to have these numeric values in a categorical format, yeah, unless when you're grouping them. But if you want to sort of like just return a numeric value, we have so many numerical values. And so it's a bit hard to create categories for all these numeric values. And so in that case, that is called a regression task. So if as you go, I guess, into this whole machine learning study, you realize that there are a couple of algorithms. Some of the algorithms are known as classification algorithms. In other words, they can only classify, whereas there are those that can do both classification and regression. But still, on the other hand, we have those that can only regress. Okay, so as we move into the unsupervised learning, so I just wanted to give this example. So we could have a data type that, a data set, sorry, that we can deploy, or we can employ the use of both supervised learning algorithms and unsupervised learning algorithms. So this data set, we are going to look at it when we get to the point of the notebook, but this is referred to as the IRIS data set. It was basically around making a prediction on those different types of flowers that are there. But if at all we are looking at it in an unsupervised learning way, we have to eliminate Y. And in that case, Y is the label. So we only have to use the features, or we only have to pass the features into the model so that it learns the representations, the patterns, and then it creates clusters. For example, if you're going to cluster the data. So in unsupervised, we are saying that there are we do not have any predefined or known set of outcomes. In other words, we don't have labels. So we need to get the data and look for those hidden patterns and the relations that are in the data. So a typical example is clustering. In other words, it's one of the common methods that are used under unsupervised learning. So something like this, that at the end of the day, we can be able to create these, let's say, 3 different clusters that you see in this small visualization. So let's look at cluster analysis as a form of unsupervised learning. Eugene, do you want me to take any questions, I guess? Or should
no,
I?
not at all.
Okay.
Yeah, there's one question from Ayob. He's asking which deep learning algorithm is suited and appropriate for disease classification using CSV file. I think this one was meant for Samiha, I think.
Mm-hmm.
I think so. Anyway, we shall deal with it. Let's first continue, and then we shall deal with Ayob.
Okay, let's go ahead. Yep. So the unsupervised learning method that we're going to learn about is clustering. To be specific, K means clustering. And for example here, if we have this type of input data, so this is just some simple data, which is around fruits. So you can see we have 3 different types of fruits. And the idea is that if we pass this data in the model, it should be able to see the pattern. And then at the end of that day, create for us these clusters. In other words, group these different types of fruits in the clusters that they belong to, something like that. So clustering basically refers to a grouping of objects based on the information found in the data that is describing the objects. Because on each instance in the data, or in each data point, you have a couple of features. So you want to see if at all these data points are related in any way using the attribute data or using the features that are in the data itself. So the motivation or the goal is that ideally you know that objects that are belonging to one group, objects in this case are the instances or the data points. So the data points that belong to one group should be similar to each other, but then they should be different from objects in another group. I'm assuming if at all we are doing some form of exclusive clustering, whereby each data point has to belong to only one cluster. So all the data points or all the objects that are belonging to one group they should be similar as they are different to objects in another group or in another cluster. Yeah, so clustering basically deals with finding a structure in a collection of unlabeled data, that the data is not labeled, but you're trying to establish the structure within that data, which we refer to as the hidden patterns or the representations within the data. So there are different examples of clustering methods. We have what we call k-means clustering. We have fuzzy or c-means clustering. And then we also have what we call hierarchical clustering. So when we go to the part of trying to code this out using the k-means clustering, you'll find that we are going to use a package that is called scikit-learn. I think some of you have heard about it. Those of you who have used Anaconda. So scikit-learn, it involves, or it has so many of these classifiers, from supervised to unsupervised, even the techniques that we use to do feature selection, and also determining what features are relevant, etc. So why I'm highlighting this is that you'll find yourself in a place whereby you're just writing 3 lines of code or 5 lines of code, but it's sort of like a black box experience. You're not really sure of what is going on within those 5 lines of codes. So part of this tutorial is basically to help us to understand from first principles that, for example, how does k-means work? If I'm to map from input X to Y, how do I get there? Something like that. So let's first look at some of the use cases of clustering, or areas in which clustering can apply. So there is what we call marketing, and I think this is important for different companies or for different organizations. I think you've seen it in telecom companies where they try to market their products, but there is what we call target marketing. So target marketing comes in basically when you're trying to target a particular group of people. But ideally for us to do that type of marketing that we call target marketing, then we need to understand our customers. We need to personalize the clients that we have, to understand them. What are the similarities in case they are there anyway? What is the likelihood that this customer is going to, for example, purchase this kind of product, this kind of bundle, etc. So that there is that type of marketing that we call target marketing. And so it comes as a result of after you've been able to distinguish your clients or your customers, and then you've been able to create the clusters. Then the other is insurance. So within insurance, I'm assuming if I told you have health insurance. So you can have these different types of clients, those who are prone to health, a particular disease, and then you can also have those ones maybe who are just applying for insurance, just. So you can create these different types of clusters and maybe say that those who are prone in terms of like they're susceptible to having issues with their health, you can decide to build them in a different way. I guess if that can help you to sort of like maximize your products, something like that. So that is also some form of clustering that we can do under insurance. Then there is what we call land use. So there is a database which includes spatial and temporal data, whereby we are able to know, for example, in eastern region, in the eastern part of Uganda, this is what the land is used for. So maybe we have a residential part, maybe we have a part where people are using the land for farming, maybe we have an industrial part, etc., all that. So we can be able to create these clusters of land use. And I guess this is also of benefit to organizations such as NEMA, because you might find instances whereby we have people building in swampy areas or people building in areas where they're not supposed to build. But if we are sort of like able to to pick up this information in the GIS database, and then we correlate it with what is happening on ground, then we can sort of like create these useful clusters that we can maybe use in terms of understanding, is the land used for actually the right purpose or wrong purpose. Then the other studies around seismic studies. So seismic studies are around oil and gas exploration, but also understanding the areas that are more likely to be affected by an earthquake in case there is one. So still this is also around studying the spatial data that is available and at hand, but also understanding what lies beneath a given, for example, land surface in a given region. Do we have this region containing so many minerals? Do we have this region containing, for example, a lot of groundwater? And so it's most likely to be affected by an earthquake, all those different elements. And so you'll find that all these different studies, much as they might appear a bit abstract, etc., but all of them, there must be relevant data for you to be able to do what? To carry on with this case study. Yeah. So there are 3 different types of clustering, and the other clustering methods that we saw from a few slides before this, they come from these different types of clustering. So there is what we call exclusive clustering, and with exclusive clustering, you're saying that an item belongs to only one cluster, but not several. So in that case, a data point can only be in one cluster. So K-means does this sort of clustering, which is called exclusive clustering. And this is just a small example of it, that if I have data points here that have color-coded orange, they will all belong to that cluster 0. If I have data points that have color-coded blue, they will all belong to that cluster named 1. If I have data points color-coded purple or black, they will all belong to that cluster 2. But on the other hand, I can have overlaps. And in that case, I can have a data point belonging to multiple clusters in case, let's say that is the type of analysis that I'm doing. So here it's the degree of association with each cluster that is known in that case. So an example of a clustering method that is under this type of clustering is what we call the fuzzy or the C-means. So at the end of the day, you sort of like have this kind of representation that, for example, here we have 2 instances or 2 items that belong to both cluster 1 and cluster 2. So that type of clustering is also available. Then the third type of clustering is what we call hierarchical clustering. And with hierarchical clustering, you sort of like have what we call a parent-child relationship, or you have like a tree-like structure. And so you can sort of like build a hierarchy of clusters. So an example here can be under when you're doing some form of document clustering. So for example, with document clustering, you can sort of like do what we call topic classification or text classification, whereby with topic classification, you can have a topic hierarchy. That, for example, if my topic is COVID-19, under COVID-19, I can have different aspects. Maybe I can have an aspect of SOPs, I can have an aspect of COVID impacts, an aspect of, so all those different elements can sort of like be topics on their own, but you find them, they are sort of lying under the main topic, which is COVID. And you might find that even COVID is lying under a main topic, which is health. So that form of clustering could be hierarchical clustering. So with hierarchical, we have 2 approaches to that. We can have the agglomerative clustering type, which is a bottom-up approach. And with that, each observation starts in its own cluster, and a pair of clusters as merged as one moves up the hierarchy. So in other words, you begin with a smaller unit, and then you keep on merging them as you move up the hierarchy. Then we can have the divisive, which is a top-down approach, whereby you have all observations starting in one cluster, and then these are split in 2 different clusters recursively as you move down the hierarchy. So sort of this, that we can start from up, which is top down, or we can start from down, which is bottom up approach, something like that. So let's focus on k-means clustering. So k-means is one of the simplest algorithms, and it's an unsupervised learning method that is used to solve clustering issues based on similarity between the data points. So ideally what happens is that with k-means, we have to divide the data into what we call k clusters, yeah? And so in that way, the algorithm itself depends on two inputs. It depends on k, which is the number of clusters that you think are in the data or that you would want to extract out from the data. Then on the other hand, it also depends on the data itself, which is the training set. So you can see the difference between the training set of an unsupervised learning algorithm and the one that we looked at under supervised. So with unsupervised, the training set here only includes the features or the attributes. These are the x variables, x1, x2, x3, up to xm, this variable that I have here. Yep. So this is still just an example that I'm assuming that I have this total population, and from this total population, I can create 4 clusters, still depending on the use case that I've decided to create, to work with. So at the end of the day, I must be able to extract out these 4 clusters. Group 1 here, group 2 here, group 3, and group 4, something like that. So now as we go down, we want to have an understanding of how are we able to create these clusters from the data. But as we do that, we can have an example from real world or ML in real life. So an example here is what we have on Google News, whereby k-means is used to automatically cluster news stories about the same topic into predefined clusters, yeah? That, for example, if I make a search about this policy, the RFBO policy, then I can have these different topics coming up, which are in form of hyperlinks. But now you'll find that there are specific elements here, there are specific elements here, something like that, yeah? That's a sample. Then another sample case study would be, imagine you want to build a school in a given location. What is the baseline information required to aid you in decision making? Yeah. So you want to build a school in a given location, and you know it's important because you wouldn't want to spend a lot of money, a lot of time, and then at the end of the day, you do not have students, etc. So what is the baseline information required to aid you in decision making? So here, if we sort of like maybe say that the baseline information that we are going to use in this case is sort of like residential. We are looking at information about different residents. And so we can sort of like say that we need to find specific locations to build schools in this area so that students do not have to travel much. So if we have this as a screenshot of the information that we've captured, assuming that this is a settlement for this particular location, same thing here, same thing here. So each data point here is maybe representing a house or a homestead, something like that. So if we have this information, then it can aid us in decision making, because at the end of the day, we can say that maybe if we have a school here, then this population is well catered for. If we have a school here, this population is also well catered for, the same thing here. Because I'm imagining maybe you're looking at a day school, a primary school, whereby you don't want the kids to travel a long distance since they are coming from home, all those different elements. So you'll find that the baseline information here that was captured is maybe how many people do we have in a given location. And if we have those people in that given location, I guess part of that data that is collected during those census activities, if we have people in that location, what age or most of the homesteads, do they have like kids, or do they have like maybe most of the kids have already done their primary, things like that. Yeah, so you'll find that all this ground information is very important. And I guess that goes back to the point of future relevance that we highlighted on. So how does k-means work? So it involves 6, 1, 2, 3, 4, 5, 6. It involves 6 different steps. And the very first step, we choose the number of clusters, we initialize, we do cluster assignment, we move the centroid, we optimize, and then we converge. But we're going to look at these in the subsequent slides. Yep. So what happens is when we are choosing the number of clusters, or when we are defining the number of clusters, we can employ a method that is referred to as the elbow method, yeah? And the elbow method can sort of be given by this formula, which is within sum of squares. So let me just use this slide, I guess, to best explain it very well. So this is just a screenshot of a code that is used in another algorithm that uses elbow, which is the k-nearest neighbor. And the idea is that, for example, if you look at where my cursor is hovering, so on my x-axis this side, I have a couple of k values, yeah? And on my y-axis here, I have what we call the error rate, yeah? So right here, I can do a loop whereby I am going to loop through a couple of k values. So here I've set a range of from 1 to 40. In other words, I'm going to start from k is equal to 1, 2, 3, something like that. But for each k value, which is in this range, what I want to do is that I want to train the model, make a prediction, and then get the error rate. So how do we get the error rate? I guess much earlier, as we are looking at accuracy, you notice that accuracy is given by the true cases, or the true cases for either class. In that case, if I have 2 classes, negative and positive, the accuracy would be given by true negative plus true positive over 2. So if I'm to determine the error rate, then I use the false cases. What do I have under false negative? What do I have under false positive? So that helps me to calculate the error rate. And so the values that you have here are the different error rate values that were captured for all these different k values, because for each k value, I'll get the accuracy, but I'll also be able to get the error rate, yeah? So the idea with the elbow method, I guess we are familiar with that part of the hand. So the idea with the elbow method is that as the k is low, in most cases, the error rate will be high, yeah? So you can see here around where k is equal to 1, the error rate was 0.100. But as you move down, or as you sort of like increase the size of k, then you're more likely to come across your best k value. So your best k value will be the very first minimum error rate before either the curve flattens or it goes up, because the elbow is in sort of like this way. So if we are to get our k value, we look at the elbow point. We look at the very first minimum we look at the very first k value that is giving us the minimum error rate. So in this case, okay, this is not bringing out the shape of the elbow very well, but still we can be able to pick it. But you can see that the very first k value that gives us the lowest value here is around this point. Maybe it's k is equal to 7, because as we increase it now, it goes high. Then maybe it comes up, down, something like that. So I'm assuming maybe it comes up to this value again at k is equal to 42. What is wrong with that value? So that value, it has no issue, but in terms of space complexity and time complexity, it has issues. Because remember, this is something that you're going to deploy. So you don't want it to take a lot of time, but you also don't want it to take a lot of space, because ideally, at each instance, or what you call an epoch, at each training of k is equal to 1, we sort of like save that value somewhere. We have to save that value somewhere, something like that. So this explanation here is basically around using the elbow method to choose the best k value, because it helps, other than guessing that, okay, let's try with k is equal to 5, let's try with k is equal to 10, something like that. So you can just come up with a range And then you loop through the range and then visualize your error rate to basically see the very first K value to give you a minimum error rate. Yeah, so this is the explanation that we have here. And the mathematical equation here is basically now a description that we are saying that we have a data point, but then we also have the closest centroid to the data point. So the error rate in this case is given by that data point minus the closest rate, but we get the squared value so that we eliminate the negatives. Yeah, so that's that. Then after we've decided on the number of clusters. So in this case, we've decided that K is equal to 2. The next thing we do is to initialize. Yeah, and what happens under initialization is that we randomly select a centroid point. So the centroid is like a center of a cluster. So I'm assuming that if this is a cluster just below the curve, and this is another cluster just above the curve. So here there is a centroid, there is a center point to which all the clusters here must be sort of like they must kind of like converge around that central point. Or in other words, the distance from that centroid to all those other points should be less than the distance of all these points to the centroid, this other side, something like that. So we start by randomly initializing our centroids, our cluster centroids. That's the initialization. And after that has been done, then we do what we call cluster assignment. So for us to assign clusters to these data points, we use a distance metric. Yeah, we compute the distance between the data points and the cluster centroid initialized. Because like I've said, that if, for example, the blue points that you see here belong to this cluster blue, then that means that the distance from all these points, from either of these points to their centroid, should be less than the distance of all these centroids, of all these data points to this other centroid. So we compute the distance between the data points and the cluster centroids. Then depending upon the minimum distance, we kind of like allocate or we assign data points into these two different groups. But we're going to see in some simple example that I came up with in the slides. Then once we've done cluster assignment, then we can move the centroid, yeah? Because we cannot trust the first iteration. Remember the first iteration, we just randomly came up with centroids. So we need to be able to do this over a number of iterations until we've noticed that the data point is, let's say, like in cluster blue, even as we move from iteration 3 to iteration 4, something like that. So for us to move the centroid, in other words, to come up with a new centroid value, we have now to compute the mean of the data points in a particular cluster. So in other words, if I have two clusters and I want to come up with the centroids of these two clusters, then I need to compute the mean of those data points in cluster 1, because that mean value is now going to become my centroid for that cluster. Then I also need to compute the mean of the distance value of the data points, in cluster 2. And that mean value is going to become the centroid, something like that. So it's what is happening here, that we compute the mean of the blue dots, then we reposition the blue cluster centroid to this mean. And then we go to another cluster, we compute the mean of those orange dots, and then we reposition the orange cluster centroid to this mean. So the optimization part comes in that now we are now going to iterate. In other words, we are going to calculate the distance of these data points again from the data point itself to the new centroid value. So that is the part of optimizing, that we repeat the previous two steps iteratively until the cluster centroids stop changing their positions. In other words, they are in the same cluster. So once that is registered, then we converge. And ideally, we return that as the output at the end of the day. So in brief or in summary, this is what happens. Part A, we do a random selection of K centers. That is after we've defined our number of clusters. We do a random selection of K centers. Remember that center is also referred to as a centroid. Then we do a cluster assignment, which is given by computing the distance of these data points to the centroids. The one that is returning the minimum distance, then we allocate it to that particular cluster. Then we recompute the centroid. This is where we looked at getting the mean value. Yeah. Then after that, we do a cluster assignment again, and again, until when we are at a point of converging, where we've noticed that from iteration 2 to iteration 3, we actually have the same values. So this is a simple example that I want us to go through to be able to understand what has been happening on the previous slides. So assuming you have 8 data points within your data, and you've decided that you're going to have 3 clusters. So these 8 data points, let's assume they are representing locations. But at the end of the day, these data points belong to, at the end of the day, these data points can belong to either of the 3 clusters. So in other words, we want to cluster them. So the very first step, we say that we randomly select a center for each cluster. And from our case that we have here, we can choose point A1, A4, and A7 to be the clusters of the 3, to be the centroids of the 3 different clusters respectively. In other words, A1 is going to be the centroid of cluster 1, A4 is going to be the centroid of cluster 2, and A7 is going to be the centroid of cluster 3, okay? So that's the first part of randomly selecting. Then in the second step, we are going to calculate the distance between the observations, and then we use k-means to cluster these observations. So the distance is given by this absolute formula right here, that we get the x2 minus x1, but we get the absolute value, plus y2 minus y1, still the absolute value on these 2 points, point A and point B. So in other words, point A can be any data point, as point B is a particular centroid. Then for us to do cluster assignment at the end of the day, we need to know what cluster centroid gave us the minimum distance, because we shall put an observation in a particular cluster if at all its centroid is the one that gave us the minimum distance. This is what we are highlighting here, that if the minimum distance of a particular data point is from cluster 1, in other words, it was obtained using cluster 1 centroid, then that point will belong to cluster 1. So this is an example still of what we have there, that these are the points we have, A1, which is 210, A2, which is 25, A3, which is 84, like that, okay? Remember, we already decided on our clusters, that cluster 1 centroid, we already decided on our centroids, sorry, that cluster 1 centroid is 210, cluster 2 centroid is 58, and cluster 3 centroid is 12. Okay, so this step 2, which is described here, is the one that is giving us these values where my cursor is hovering. And to just walk through these values, we are saying that we are going to get we are going to measure the distance from this point to this centroid point. From this point to this centroid point, and we populate the values right here. So if I go through this, it gives me 0 because I'm getting 2 minus 2 plus 10 minus 10, which is 0. Then here, the 5, how do I get the 5? I'm getting 2 minus 5, which is 3, because I'm getting the absolute value. Then that 3, I'll add it on that 10 minus 8, which is the 3 plus 2, giving me 5. Then this value here, I'm going to get 2 minus 1, which is 1, plus 10 minus 2, which is 8. So I'm getting 1 plus 8, which is 9. So at the end of the day, on point 1, if I'm calculating the distance of point 1 from all these different centroids, this first centroid is returning the minimum distance, because if I look here 0.599, sorry, 0.59, the minimum distance is 0. So this the centroid of cluster 1 is returning the minimum distance. And so that is why you see that A1 was allocated cluster 1. So it's what I've just described here, that after the distance has been calculated, then we use the minimum distance to determine the cluster for the observation. In other words, to assign it a cluster. If the minimum distance is from cluster 1, then the point is put in cluster 1. So still, that is the description that we had right here, that depending upon the minimum distance, the data points are divided into two groups. This case, 2 groups, because we started at the point where we said that our K is equal to 2, okay? So we do the same thing on the next point. We calculate the distance of this point 2,5 over these cluster centroids. So 2,5, 210, this is 0 plus 5, which is a 5. Then here the 6 is given by 2 minus 5, which is 3, plus 5 minus 8, that is 3 plus 3, giving me a 6. And here the 4 is given by 2 minus 1, which is 1, plus 5 minus 2, which is 3. So that's 1 plus 3, giving me a 4. So at the end of the day, A2 comes as one that is assigned cluster 3, because the minimum distance is given by the centroid of cluster 3. So the same applies to all these points here. And so at the end of the day, having calculated the distance of all these points, so ideally this is what happens in the black box of scikit-learn. So having calculated the distance of all these points from the centroids, we've been able to assign them clusters. But we are saying we need to do it again. I guess this is the point where we need to move the centroid, because the first centroid values were given by randomly assigning. So we need to move the centroid. So how do we move the centroid? We calculate the mean, okay? So cluster 1, according to this table, I only have 1 point under cluster 1, which is 210. Under cluster 2, I have 5 points. I have 5 points, which is this, and that. Which are still highlighted here. Then under cluster 3, I have 2 points. I have A2 and A7. Yep. So the third step is to calculate the new centroid, which we've referred to as move centroid. We calculate the new centroid for each cluster. We do so by taking the mean of all points in each cluster. Still, it was highlighted right here, that we compute the mean of blue dots. In other words, one cluster, which is blue dots, also the other cluster, which is the orange dots. Then we reposition the centroid of that cluster with the mean value that we've got. So still, which is what is highlighted here. So for cluster 1, we only have 1 point, 210, which was the old mean. So in that case, for that cluster, the center will remain the same, because we do not have any other data points to use when we are going to calculate the mean. So in other words, for this cluster, the centroid holds as 210. However, for cluster 2, the centroid changes because cluster 2 had 5 points. So the mean is going to be given by getting the mean of all, a summation of all x values divided by the number of points, comma, a summation of all y values divided by the number of points. So here I have 5 points. And so I first extract out the x values, which is 8 plus 5 plus 7 plus 6 plus 4, divide by 5 because I have 5 points, then comma, 4 plus 8 plus 5 plus 4 plus 9, divide by 5, still because I have 5 data points. And so this is what is happening here. So at the end of the day, I end up with a value which is 6, 6. This means that if we go to another iteration where we are trying to optimize, we are not going to continue with this centroid of 5, 8. No, we are going to reposition the centroid to 6, 6. Then we do the same thing for cluster 3. Cluster 3 had 2 points, 2, 5, and 1, 2. So this is given by 2 plus 1, 2 plus 1 divided by 2, because there are 2 points, 5 plus 2 divided by 2, giving me 1.5, 3.5. So this is the new centroid for cluster 3. Okay, so now this means that we have 3 new centroids to consider on the second iteration. We have 210, we have 66, 1.5, 3.5. And so these clusters are for, these centroids are for cluster 1, 2, 3, respectively. So we repeat step 2 and 3. Step 2, which was, we calculate the distance between the observations, and step 3, which was moving the centroid. So we are going to repeat this step 2 and 3 until clustering from one iteration to another does not change. And with that, we produce the final schema as the final clusters for each data point. In other words, what that means that here 210 holds, but if we erase this and we replace it with 66, this we replace it with, I think it was 1.5 and 3.5, yes, then we get new values here, okay? So we observe if at all there is a change from iteration 1 to iteration 2. Should there be a change, of which there is for this example, in other words, A2 is returned in a different cluster, A3 is returned in a different cluster, even if it's on a single data point, we repeat the iteration. Repeating the iteration means that we go ahead and get the new centroid values, then go back to step 2 until when we've noticed that there is a convergence, that we are not having kind of like migrations from one cluster into another cluster. So that is what happens. Yeah, so that is it with the theory. Any questions before I go to the notebook? I think I have a
Thank you.
Okay.
Yeah, thank you very much, Claire. I will really appreciate your presentation. Rosie, is it possible you type in your question? Rosie, I can see your hand up. I also saw a hand from Leon Orota. May we please have, okay, I'll make an exception for this particular moment. Leon raised his hand first. So Leon, let me see if I can allow you to speak out loud. So Leon, you can speak, please. Leon, your hand was up. Do you have to address us in any way? Okay, the next person, I saw some other hand up. Let me just see here. Sela Bay, you can go ahead and ask a question or comment. You can talk to us, please. Sela Bay.
Hello?
Please carry on.
Okay, can you hear me?
Yes, we can hear you.
Okay, first I'd like to say thank you very much for your nice presentation. So the first question that I have is about the techniques that you have discussed on the presentation, especially for unsupervised machine learning techniques. Most of the time, this unsupervised machine learning algorithms is used for clustering, for grouping something. But most of the time, especially when we are using k-means clustering algorithms, selecting the key value is so difficult. So is there any technique or a mechanism how can we select the value of k if you are using the k-means clustering techniques? Thank you so much.
To you, Claire.
Thank you for the question. I guess you might have missed that part. You just go back. So, so one of the advised techniques, especially if you're not familiar with the data that you're handling, because in cases where you're familiar with the data, then you can know that I have 5 topics within the data. Let me assume that, let's say like this is a clustering problem that you've extracted from a supervised learning case. And let's say like you have 5 topics. So if you approach it in that way, you know that you have 5 topics. But now assuming you're not sure of the number of topics within the data. So the best approach to it would be to use the elbow method, which I was indicating here. So with the elbow method, what happens is that you try to sample with a range of K values in a single instance or in a single cell. Unlike you, for example, saying like, let's say K is equal to 2, and then you see what it gives you, K is equal to 3, then you see what it gives you. So what you can do is, for example, here, we just say that you can create a loop, and just right here, I hope my screen is very clear. Sorry. So you can create a loop, and then you select on, let's say like 100 K values, assuming you have the computing power. So you can say maybe range of 1 to 100. That means that it's going to go through all those 100 different K values. And on each instance where it's training and testing with this data, it's going to be considering a given K value. So this loop here, what it's doing is that, first of all, we are setting our range from 1 to 40, and then we are initializing our classifier to I values, because those I values are in the range of 1 to 40. Then for each value, we are saying train, predict, and calculate the error rate. So like I said, accuracy is given by looking at the true cases. And if we are to get the error rate, then we have to look at the false cases. So when you look at this visualization right here, it gives us the different error rate values that are registered over these K values that are on the x-axis. That as we started with K is equal to 1, our error rate was 0.1. So 0.1 sounds to be a very small error rate, but in machine learning, that is a very huge error. And you can see that ideally we can even drop up to 0.050, for example. So the idea with this elbow method is that it helps you to visualize, or it helps you to capture the different error rate values that you're registering for each K value. And so at the end of the day, your best K value will be that which is at the elbow, because like this slide, like we can see on this slide, is that we begin from our high value, but as we increase on the number of K values, or as we increase the number of clusters, there is that very first value, K value, that is going to give us a minimum error rate. So that value is at the elbow point. And so that is our best K value, because ideally what happens is that later on, either it will flatten, and so it will not make sense to use other what? To consider other K cases, because now the error rate is constant, it's not changing. Or it will kind of like maybe increase, just like you can see here. But even if it drops again, this will be the best value in terms of time complexity and space complexity. Yeah. So the best K value can be determined using the elbow method. That's what I can answer on that.
Birone.
Okay, Sela, I think your question has been addressed.
Yeah,
thank you very much, Claire.
Thank you so much for your nice answers. Thank you.
Okay. Now, Rosie Hieromini, you wanted to address us. Are you still in position to address us? Okay. I've seen another hand. Eyob is here. Eyob, you can carry on. Eyob.
Hello?
Yes, we can hear you, Eob.
Okay, can I ask from the morning session?
Yes, I see Claire, I see Alan, I see Isaac is in. Yes, Samiha is not in.
I missed the deep learning session, and can I ask
but there's no problem. You can still ask. It's okay. Carry on.
Okay, so thank you for your presentation. And in deep learning algorithm, there are different kinds of algorithms that we use for solving of different kinds of problems. In deep learning algorithms, which kind of deep learning algorithm is very appropriate and suited for solving of classification problems using of like CSV file?
Okay, thank you for the question. Claire, Isaac, Alan. Samia is not in. Anybody can take a question.
Okay, so maybe I'll give it a try. So what happens is that the performance of the algorithm, or the performance of, not algorithm, the performance of the model is dependent on two parameters, the data and the algorithm. So I think Samiha tried to highlight that there is data that is linearly separable, and then there is data that is non-linearly separable. So the researchers, having made these discoveries, they did what? They kind of like customized some of these algorithms to cater for linearly separable data and others to cater for non-linearly separable data. So I guess it would be strange on my side to tag you to one algorithm that is good, but learning the kind of data or the structure of the data that you're handling, even if it is a CSV file, it can help you to know what algorithm to use best. And in instances where you can't maybe do that, basically find out if you're dealing with linearly separable data or non-linearly separable data, you can try with more than one algorithm and you evaluate the performance of each algorithm because you already have an understanding of the pros and cons of these different algorithms. Yeah, so it highly depends on the data because different algorithms are good with different formats or structures within the data. But
Okay.
Isaac can add on that.
Isaac, Alan. Okay, it is okay if there's no supplement. Eob, was that clear on your side? Did you get it?
I have a question again.
Okay,
sorry.
Carry on.
Which kinds of algorithms are mostly recommended?
Is that for deep learning or machine learning?
Yeah, in deep learning, from the previous question.
Deep learning?
Yes.
So for deep learning, we have CNN, which is convolutional neural nets. I think there will be a discussion on that tomorrow. Then we have the RNN, which are very common among others.
Okay, can you use those algorithms for classifying like CSV files?
Yes, you can. Yes, you can. So those are specifically for supervised learning, classification problems. So you can.
Okay.
Okay. Thank you very much, Claire. Thank you very much, Eob. I think anybody else? I see Sela has come back with another question, but I would like to offer a chance to somebody else before Sela. Anybody else with another question? Before I give another chance to Sela. Okay, nobody else. So I'm gonna give you Sela. You can carry on, please.
Okay, thank you so much for giving me a chance again. And I have a question also from the age of perspective point of view. So what he said, as I understand from him, is just he already has a data on your hand, which is CSV files, and he wanted to develop some classifier models that can be used to classify some disease, I think. So what the response says that convolutional neural network is more preferable, right? But CNN is more specially designed for, it's more preferable for image data. So why CSV files is more, why CNN is more preferred for some CSV files? Thank you.
Sela,
Yes.
I didn't get the question clearly, please.
Yeah, what I've said is.
Eugene, can I attempt to answer?
Okay.
I'm not sure if I got the question right, but I'm assuming I got it right. So I didn't say that CNN is preferred for CSV, but what I meant is that it can also be used for data within CSV. So much as, for example, in machine learning, there are computer vision algorithms or algorithms that can be used to tackle imagery data. You can also find other algorithms that can be used to tackle imagery data. And I guess that goes back to the point of you need to learn the data that you have at hand and what algorithm works best with that data. So data in terms of representation, but also in terms of the type of data.
Okay.
Yeah, something like that.
Yeah, look, just when you say machine learning and deep learning, as far as I know, just in deep learning, there is a CNN. A CNN has two blocks. The first one is feature extraction blocks, and the second one is a classifier blocks, right? So in the classifier block, the CNN is used ANN or artificial neural network. There is also ANN in machine learning. So
also what?
In machine learning, there is also artificial neural network. ANN.
Okay, Sela,
Yes.
I'm sorry to cut you short. As of now, as we speak right now, our time is over, but I'm going to run a quick poll to just ascertain if we would like to really do a practical session. So all the attendants will actually receive a screen right now. Okay. Then from your polling, we shall be able to confirm if we are going to carry on with the session so that Claire can give us a practical session. Please look at your screens. You should be able to see something going on. If you need this to be taken to the practical side of things, let me have a look at this and then we can, okay, yeah, we shall come back to you, Sela.
Okay, thank you so much.
All right. Okay, we practically have 1 or 2 minutes to finalize this, and so far the yeses are more than the nos. Yeah, so let's see how this goes. Okay, all right. So 85% of us are in agreement that we continue with this session. 15% would like to retire. Quite unfortunate that we won't have we won't have you guys in, but I think the vote is clear that we should be able to continue. So Claire, please carry on with the practical side. I think we shall take more questions. I've seen a hand from Babirye, but let's go in for the practical side of things first, then we can resume on the Q&A. Please, Claire.
Okay, let me share my screen. Okay. Can you see my screen?
Yes, I can see it.
Okay, so this practical series has two versions. I guess it has the supervised learning version and also the unsupervised learning version using K-means. Okay, so for this case, I used the IRIS dataset. And like I said, the IRIS dataset, so the idea is basically to see if we have these different features that we've extracted from this data, can we be able to tell the plant given a new instance? So there are three different instances that we have, or actually three different types where all the instances can belong. So we have the versicolor, the virginca, and the setonsa as the three different classes just right here. And we have 50 instances within each class, giving us a total of 150 instances. So this is just a code to depict the visualization right here below, which includes the different instances from each plant or from each category that we have. Okay, then the format of the data that we have. So this is an interesting data set because someone could choose to use the imagery data itself in terms of like classifying the data. But in this case, we chose to use the features within the data, and the features include the sepal length, the sepal width, the petal length, and the petal width. So why these features? So the idea is that these features were selected because given these features, we can be able to tell the type of the iris plant. We can be able to tell that this belongs to versicolor, or it belongs to setonsa, or it belongs to virginca, something like that. So ideally, that is why those features were selected. So we start by importing the necessary packages, as still the previous speakers highlighted on these packages. And if you have already installed Anaconda comes with these packages. So you just need to open your notebook via command line or whatever that is you're comfortable with, and then you import the necessary packages. Still, they highlighted that we can use the alliance name, and the commonly alliance names are these ones: NP for NumPy, PD for pandas, SNS for seaborn, and PLT for matplotlib.pyplot. So still, the reason why we prefer these is because that every time you want to use this NumPy package, you do not have to use the name NumPy, the entire name NumPy. You can just refer to it using the alliance name, which is NP. So the same holds for all these other packages. Then the use of this very last line of code here, the %matplotlib inline, is to help us to have these visualizations within the notebook. Shouldn't we have it, the visualizations will come up, but as pop-up windows or in a different screen. So that is the use of this %matplotlib inline. So I started by importing the data into this notebook, and something like this. So I guess you've noticed that you can have a path here. So it depends on where exactly your data is. So if I have, I don't know, what screen can you see now, Eugene? Eugene?
We can see.
What screen are you seeing? That's the question.
Home.
Just a second.
Okay, yeah. So if you just have your data within the folder where the notebook is, just like you see here, then you don't need to mention the path. You just need to refer to that data. But if at all that's not the case, then you need to specify the path, something like that. Okay, I hope I'm back to the notebook. So that is what happens. Then this is just printing the very first 5 rows within the data, referred to as .head. And I've just called my data variable iris underscore data. So now the data, when we sort of like see that, or even when we go below here, using .columns, we can see the columns within the data. We have ID, we have sepal length, We have sepal width, we have petal length, we have petal width, and we also have the species. So, so all these different values here, the numeric values apart from ID, were captured in centimeters. I guess that's why we see the cm there. But at the end of the day, we could sort of like maybe even think about plotting the data using, let's say, 1 to 2 features. So this is a plot of sepal length vis-a-vis sepal width. Yep, something like that. Then there is something called Andrew curves, which is also a package within pandas.plotting, which helps us to visualize multi-dimensional data, sort of like to visualize the data on all these features, because here we have more than 2 features, but on this scatter plot, we've only decided to go with 2. So we could have all of them embedded within what we call the Andrew curves to sort of like return something like that you're seeing. Yeah, but these are just different formats of data visualization. So I'm starting with a part of supervised. So we begin by splitting the data because in this case, I only have one CSV file that I'm going to work with. So I split the data using the train test split method. And yeah, right here below. So as I walk into that split, I also need to define what is my X and what is my Y. Remember, we said X, those are the attributes or the features within the data, and Y, those are the labels for the data. So I can extract out the features by using the iloc method. What this one means is that it's going to return all the rows and the columns minus the last column. So it's sort of a row by column, but excluding the last column, which is referred to as -1. Then this one, the one that returns the last column, which is Y in that case, what happens is we specify .iloc, and then we specify that for all rows, let's return the values in the last column. So this is just another way of splitting the data, that is XY, but there are also other ways in which you can do that. Then once we've done that, we can now create 4 different variables. So the 4 different variables are going to hold first the training data set, which is X train and Y train, then also the test data set, which is X test and Y test. Okay, then within that method, yes, we pass X and Y, whereby X are the features and Y are the labels. Then we also specify the test size. So in this case, we are saying the test size is 0.2. So it's going to get 20% of this iris data, and it will put it under the test cases, that is X test and Y test. And then here we used a simple algorithm for supervised, which is called decision trees. I guess one of the reasons, okay, we've not been really able to visualize that, but decision trees is very good with non-linearly separable data. Non-linearly separable data is that data whereby you cannot find a single line that can separate the data, because ideally we say with classification, we must find that decision surface or that boundary line. So with non-linearly separable data, we could employ the use of algorithms such as decision trees, because decision trees, what it does is that it helps us to make the data linearly separable by coming up with a couple of decisions. And so at the end of that day, we are able to actually find a decision surface for the data using these different decisions constructed from this classifier. So the first part here, we import the decision tree classifier from sklearn.tree, which is a package in scikit-learn. Then the next part here, we just import the necessary evaluation metrics that we shall use to do what? To evaluate or assess the performance. After that, we instantiate an object which is going to hold the decision tree classifier. So this object, ideally, it's going to contain the underlying function of decision trees. In other words, whatever knowledge that you have under decision tree, the idea of getting the entropy, getting the information gain. So the mathematical function of decision tree classifier was pre-coded in this script called decision tree classifier. And so it's what we are sort of like instantiating within this object, iris model. Once we have our object, then we can fit. So .fit is a method that facilitates training. And because we've highlighted that with supervised learning, we train with labeled examples, that's why you can see that we have two variables. I guess you have the code, you can try to remove one variable and you see what happens. So yeah, so that's why we see that we have X train and Y train. And at the end of the day, we have a model that has been returned. So ideally, I guess if I had the necessary packages for visualizing this decision tree, if in case I do a visualization of the decision tree, this classifier, it returns a tree that contains a couple of decisions that can be, that can facilitate me in classifying those different species or iris plants. Once we have the decision tree classifier or the model that has learned the representation within the data, then we can make a prediction. Now with prediction, we said you pass in a test set, a new set that it has not seen. And so that is why the very first thing that we did was to split, because we didn't want to pass in this data and then we have to test on it again. But you can see now how the test phase differs from the training phase is that at the point of testing, we only pass the features. We do not pass the labels. Still, you can try, if you downloaded the code, you can try passing the Y test and then you will see what will happen. Yeah, so we predict, and now here the predicted values have been stored in a variable called yPredict. Once that is done, we can now evaluate. So one metric that we have is what we call a classification report. So this is just a summary of what we have in terms of precision, recall, F1 score, accuracy, the macro average, the weighted average, all that. So a summary of this. Then we can also have what we call a confusion matrix as another evaluation metric. So a confusion matrix, it helps us to visualize or to capture how is the model performing on each class. So you can see we had 3 species. We had Setosa, Virginica, and Versicolor, I think. So that's why you can see that we have a 3x3 matrix as a confusion matrix. So the number of rows and the number of columns returned in a confusion matrix depend on the number of classes. If we have 5 classes, then it will return a 5x5. If we have 2, then it returns a 2x2. But also on the other hand, we can get the accuracy, which is given by getting the true cases and the true cases for all the classes divided by the total number of test classes. So in this case, that's why you see that we pass in yPredict and yTest, because we need to know how many true cases do we have under each of those species, so that at the end of the day, we end up with this 0.96 or the 96%. So a better way of how to visualize this, you can use a heat map. I guess that was the whole idea of importing this other visualization package called Seaborn. So we can have a visualization such as this, where we have different intensities depending on the scope maybe. And on a confusion matrix, you will have a main diagonal. So you ideally want to have the maximum values on the main diagonal, because the maximum values, those are the true cases for all the classes. In other words, that is where the actual or the true and the predicted for either class kind of intersect. So you can see this box here where my cursor is hovering is the true, is where true label for Setosa and the predicted label for Setosa mean. In other words, this means that 11 were actually Setosa and have been predicted as Setosa. As on the other hand, 13 were actually, say, Versicolor and have been predicted as Versicolor. Then on the other hand, Virginica, there were 5 and 5 have been predicted, much as 1 was wrongly predicted as Versicolor. So confusion matrix provides us with those details that we use to calculate the precision and the recall. Yeah, and I guess still to highlight what Samiha was saying, that accuracy can be misleading, is because accuracy does not give us details in terms of the false cases. Why? Because it only considers true cases. Yet, if we are to fine-tune the model, we need to understand where is it getting it wrong, and also to understand why is it getting it wrong. So you can see here that Setosa and Versicolor, it's performing well, whereas in Virginica, it's not performing well. So maybe we can think of different scenarios. Could it be because Virginica has less data? Could it be maybe there is this high similarity between these two classes, so on and so forth. So then you can sort of like go back behind and sort of like troubleshoot, because you've been able to understand where is it getting it wrong. So that is a case of supervised, specifically decision trees. But on the other hand, we can also look at the same problem, but using clustering analysis. So this data, the IRIS data, is available under sklearn datasets or scikit-learn datasets. And so we can load it via this, load IRIS. Then here, I just import k-means. Then having loaded the sklearn datasets in specific the IRIS data. So the reason why we say from sklearn.datasets import load IRIS, because if we stop here, assuming I delete this, it means that it's going to import or to read everything, sort of like actually, if I have import sklearn dataset, something like that, it means that it's going to import all the datasets, and there are quite a number of sklearn datasets. So there you're just overwhelming your memory already. So that's why you need to be specific and import that which you need. So it's the same thing, that there are other clustering methods, but I'm mainly interested in k-means for this scenario. Then we load the data from this. So you realize for these two to run, for this to run especially, you'll need to be connected to the internet because you're loading it from a URL. Then I can create a data frame, but in this data frame, I specify .feature names. So just in case you're wondering, why am I importing it, yet I already have it above. So there are two ways. I can either use this approach, whereby I end up with only the features, which are sort of like identified here as feature names, or I can go back up and then I find a way of sort of like eliminating the last column. So either would work, but this was just to point us to a scenario where we could refer to the dataset directly from scikit-learn. Then having done that, when we are instantiating an object, so when we are instantiating the object, k-means using the classifier k-means that we've imported, we have to pass in different parameters, okay? So we pass in parameters such as the number of clusters. Here, okay, in this case, we already know that there are 3 clusters, something like that. Then we initiate to k-means plus, then we can also set the maximum iteration, and as well as those other parameters that we have there. Then once that is done, we can predict, we can sort of like make a prediction now, yeah, using our X data, because our X data is, that's where we only had the features. Okay, and then from that, we can sort of like be able to extract out data per a given label. Yeah, so sort of like extract out data on iris.setosa, extract out data on Versicolor, on Virginica, and then at the end of that day, we can also be able to stack this data together to see, because this is like the output, yeah, from the prediction, the YK means this is what has been predicted. Then we can also be able to get the centroids, because once that iteration is done, or once the classifier has given us the output, it also gives us the centroids. So you can already see from here that we have 3 different centroids, first of all, because we say there are 3 clusters, but now we can merge the predicted values in this scatter plot with the centroid values to sort of like see something like this. Yep. So, so the centroid for this blue, which is the Versicolor, is this. The centroid for Virginica, which is green, is here, and then the centroid for Iris setosa is this, something like that. So the insight we can get from the scatter plot is that the model's accuracy is determining setosa and Virginica more to versicolor. So something like that. So you can see that here setosa is actually coming up to this side down, but still, like I said, these are just predicted values that we are getting from the k-means classifier. So that is what happens if you're coding k-means. Yeah, that's it. Eugene, back to you.
Okay, that's thank you so much for the presentation. Now, there are a lot of questions that have come in through, and all the panelists are now becoming active on the chat. In the meantime, we would like to just address a few questions, live questions, and I see already we have Bereket, who is ready to go in for the first question. So other facilitators are helping out on answering some of the questions. I think Claire can come in and clear some air because some people are asking directly from what you are showing. Leon, let me just see this first. We have Leon Orota. He's asking, what are your suggestions to solve the memory limit error when you're running ensemble ML algorithms such as EE classifier? So there's somebody, so let's come back to that, but there's somebody who touched on the code itself. Okay, Isaac Ketungu is asking, can they explain code line 17 output as per the dataset? So which one is the best evaluation metric? So this one is directly onto the code. So Claire, I think you need to take this.
Okay, let me share the screen again. Just a minute, sharing. So, okay, so line 17, I guess it's this, the classification report. So line 17 or code 17, it gives us details on these different metrics, what we call precision, what we call recall, what we call F1 score, and then what we also call support. So, so precision and recall, okay, all these different metrics, they sort of like give us specific information about each class. So for example, with precision, we try to find out the accuracy of the positive predictions. In other words, how did it perform in predicting this class, Iris setosa? How did it perform in predicting this versicolor? How did it perform in predicting Virginica, something like that? And it's sort of like the same thing with recall. So we want to specifically understand, did it do well in predicting a particular class? That is the idea with precision and recall. And then these others, F1 score and support, you'll find that they're given by what? They're still given by these two primarily matrices, the precision and the recall. Then accuracy, we've already highlighted on what accuracy is. So we just look at the true cases for all the instances, and then we find out what happened. Yeah. Then we have macro average and weighted average. And I think the idea with this is that we can sort of like, for example, average, let me say like if I run this part of predicting more than once, we can sort of like average the numerical values in terms of the true cases and the false cases that we get. under what we might call macro average and weighted average. Yeah, but it's ideally a summary of predictions made by the classifier, much as you can do more reading around it to have an understanding.
Yeah, okay. In the same regard, he continued and asked, so which one is the best evaluation metrics?
So which one is the best evaluation metrics? So ideally the best is this confusion matrix and the ROC. Sami had mentioned the ROC. Why? Because these values, the values that we have here, the precision and recall, are given from these, the true cases, the false cases. So once you have an output of this, or once you have an understanding of these values that you have here, then you can be able to calculate this. Yeah, but on top of accuracy, most people go ahead and find out the precision, they go ahead and find out the recall, then they also go ahead and do the ROC curve.
Okay, thank you very much. I hope Isaac has gotten the gist. Next question is, what role can machine learning play in product regulation agency? I will give this to our chairperson, Mr. Bruno, to address. What role can machine learning play in the product regulation agency? Mr. Bruno, we have a question for you. What role does machine learning play in the product regulation agency? That is a question by Paul Asare. Isaac is appreciating and is thankful for the answer. It is adequate. Our chairperson is not here. Anybody among our panelists, anybody who would like to go in to attend to Paul Asare's question, what role does machine learning play in the product regulation agency?
I think I can attempt.
Okay.
Do you want to break down product regulation agency? Because I think it includes so many things.
Yeah, it is actually a very big aspect. If we go into it, probably he will come and elucidate. But from my thinking line, he might be specific with only things that might actually require the AI in essence. But with the bodies, including maybe, I'm not so sure about any agencies in Uganda. I don't know if this is international or locally based. So maybe Paul can come in and elucidate on which agency you're actually referring to, so that we can actually give this. Maybe we can give a general answer. Claire?
Yeah, so it's a bit interesting because I might not be able to generalize on the whole agency, because you'll find that
okay, he has responded.
AI,
He has responded. He's saying he's referring to food and drugs regulation.
to food and drugs regulation.
Drugs regulation.
Oh.
Paul, is it possible we give you a chance to express this on live?
Yeah.
Let me just, So Paul, you can talk to us, please. Paul, you can unmute and you talk to us, please. Paul, unmute your mic and you talk to us. We need to address this and we move on. Okay, so as Paul is coming in, we have, I think, two more questions that need to be addressed. Leon Orota is also referred, this should be Isaac. Isaac, take this question from Leon Orota. Leon is asking, what are your suggestions to solve the memory limit error when running ensemble machine learning algorithms such as EE classifier, the granite tree boost over extensive land areas. Isaac? Isaac, are you in? Yes, Isaac. Isaac, you can carry on, please. Okay, I can't reach to Isaac. He's the one who handled this section. But we shall put this into stock so that we can have this addressed. This is to Samiha, but she's not around. When do we use ANN and CNN? I think we can attempt this, Alan or Claire. When do we use ANN and CNN? Okay.
So I guess we've kind of like tried to highlight that on CNN and RNN. So that different algorithms depend on what exactly are you trying to do and what data are you using. But the idea is that with deep learning algorithms, if you have sufficient data and the problem is well defined, then yeah, then ideally you can use the ANN and CNN. But you need to sort of like have an understanding of what is ANN good at, what is CNN good at, and what problem are you solving with what data. So it depends on all those different factors.
Okay. Something related to that from Selabe is asking, in machine learning, there is ANN. In deep learning, the classifier is also ANN. So what makes it different if we pass a .csv file to this classifier?
So what classifier exactly?
He's saying in machine learning, there is ANN. In deep learning, the classifier is also ANN. So what makes it different if we pass a .csv file to this classifier?
Okay, so I don't think the question is very clear. So so ANN is artificial neural network. I suppose that's what she's meaning, and CNN the convolutional neural network. So okay, let me just get to the question because I need to understand it.
Just checking the QA.
It's Q&A.
Yeah, Q&A. Question by Selabe.
In machine learning, the ANN. In deep learning, the classifier is also ANN. So what makes it different if we pass .csv file to this classifier? So machine learning algorithms are different from deep learning algorithms. And this does not mean, for example, the example we're looking at here, we are looking at use of machine learning algorithms. But it does not mean that we cannot use deep learning algorithms. So we can still use deep learning algorithms on the same data. But what we have to keep in mind is that deep learning algorithms learn well with vast amounts of data. We're talking about 1,000 data points and above, etc. But it does not mean that if the data has gone through an ML classifier, it cannot go through a deep learning classifier. It can. And yes, you can be able to see the difference with the results yielded from the ML model or the ML classifier and the results that have been obtained from this deep learning model. I hope that answers your question.
Okay, thank you very much, Claire, for being with us for this long, for these 2 hours. We really appreciate your time. I know we have a pending question by Paul. He has tried to put on some detail. We needed some clarity.
saw,
He added in, so he was saying this is in regard to, so he was talking about machine learning in policy agency, and he said specifically marketing, no,
Eugene,
food and drugs. And in
yeah,
food and
so
drugs,
Alan attempted to respond to that. Ideally,
okay.
what happens is that machine learning, we are trying to see, can we come up with data-driven decisions? In other words, we are trying to see, can we go to the data, evidence some facts within the data and influence policy? So Alan responded to it on a generalized part because the question is still generalized. So it depends on what exactly does he want to find out in regards to foods and drugs. Is it about validating whether a specific food type or a drug type is can be consumed? Is it about maybe accepting it in society depending on the purchasing power? And in that case, we have to look at how many people have used it, what are the side effects, all those different elements. So it depends on what exactly under foods and drugs. But if we are generalizing, I think on a general part, I would also put it the way Alan has put it.
Okay, which will also apply to sales and marketing, as Innocent wants to know. So yeah.
So for Innocent, I think we had that example within the data still. Can I use machine learning in sales and marketing, especially where I have a lot of consumer data? If yes, how can I go about it? So yes, yes, you can. But under sales and marketing, what exactly do you want to do? So I gave an example that in marketing, you can do what we call target marketing, whereby you're now going to see how can I target a specific group of people. For you to be able to target a specific group of people, you need to start at a point where you can personalize. So in other words, you are able to say, let me say that, can I actually say that I have 5 different types of customers? Customers who are interested in this product, customers who consume at this time of the day, customers, something like that. So yes, you can, after understanding the different representations within the data, and still, since we are talking about data-driven decisions, one thing that you have to know is that the features within the data help you to understand it very well. Because you'll find that at times you have to use one feature, maybe now see how does this feature complement the other feature, things like that.
Okay.
Yeah, so if, okay, yeah.
Well, yeah, that's adequate, I think. It's adequate. Yeah, I'm very proud of our first day today, and I would like